Hi everyone. I'm Victor, and for the better part of the next hour, we're going to talk about the quest for a better crash. So just a reminder, we're all here in Remo, and due to the nature of the delivery medium and the streaming delays that are involved, I would prefer that you hold your questions to the end of the presentation. You can write them in Remo in the Q&A tab and upvote them during the talk, but I'll take them at the end, at the very end. Okay, so a bit about me. You might have heard about some of you about Advanced Installer. You might be using it, or maybe Clang Power Tools. I'm going to be talking today in the context of the work that we've done over the past 15 years within the Advanced Installer team. And I'm going to showcase some of the tooling and learnings that we did experimenting with various strategies in the quest for a better crash or a better stack trace. So this will be a vignette in 3 parts. Remembering the crash, how to roll your own, and maybe for next year's a few words about the future in terms of stuff coming in the C++23 standard. Just as a disclaimer, this will be 99% talk about Windows and technologies on Windows. Just the third part of the talk will touch upon the proposal that was accepted into C++23 about building standard portable stack trace facilities in the library, in the STL. So until we get there, it's going to be a Windows ride. So remember the crash. I think we've all been there, and we've seen crashes such as this one, albeit this is a pretty old screenshot. And some of you might even remember Dr. Watson. I would really love to see a hands up if I were physically in a room with you. Who remembers Dr. Watson and fiddling with post-mortem debugging there? It was fun. I have good memories there. And maybe the modern descendant of Dr. Watson, WER, Windows Error Reporting. That's basically the same concept wrapped into a more modern or neat package with tighter integrations into developer portal and developer services. But basically the same idea. But where do all these crashes go, actually? Is this even available for third-party Windows apps? Because I've seen those crashes and those logs being collected mainly from Windows applications that failed on me along the years since Windows 2000 up to current Windows 10. And questions that I've had over 10 years ago now about this was way before any store or Windows Dev Center being available. Can I leverage the same functionality within my app? How can we register to receive such crash dumps that Windows collects? What does it cost? How does the crash data look like? Who owns it? Microsoft stores it. What's the whole picture behind it? Those were, you might consider it, naive questions that we had very long time ago. But basically, all I wanted was this. I wanted a stack trace for any crash or problem that our users encountered in production. And because it's not always easy to actually debug remote problems, sometimes for privacy or security issues, you don't have access to do a remote connection to debug remotely on computer machines. Sometimes the log files are not enough. You have to build, construct custom builds for your application to do various scenarios or to add more verbose logging to figure things out. Sometimes the steps to reproduce the issue are incomplete. Sometimes the context really matters, or the application state before the crash. So you basically want to see all the context that your client was in when using your application, and being able to replay those scenarios or pinpoint the exact problem that they encountered. So basically, you want the same experience that you have on your own developing machine when you encounter a crash during testing or during debugging your application. You want the same experience, but for an action that took place remotely. And the answers to all those questions I had over 10 years ago turned out to be complicated. Custom registration for each app version, Microsoft symbol servers instances. If you want to deploy those on premise, it really complicates things. You have to figure out how to work with symbol servers and everything. It's doable, but in my opinion, it's a DevOps nightmare. And I'm not very keen on actually doing DevOps kind of tasks. I want to just program. And like any good programmer, I decided to build my own. You might say we're setting ourselves up for long run and possibly failures, but we were young and naive. Some goals we set out for this. It had to be quick to develop because we need it as soon as possible. We want it to be easy to integrate in our CI/CD system. No special service or symbol server setup required. We want zero footprint on client side, so we don't want to ship symbols on client machines. As it turns out, the application that we work on is fairly big, and for example, for debug build, the symbols are over 1 gigabyte, and for release build, they are close to 600-700 megabytes. So it's fairly big. You don't want that footprint on the client computer. Zero performance impact on release binaries, of course, on the happy path. And easy to use as a standalone tool on a non-developer setup box, because you want to be able to process these crash reports by engineers that are not part of the actual development teams. So you want solutions engineers, support engineers to be able to triage properly these crash reports and being able to figure out more easily the respective components and project owners that need to be notified in the triage process. And you want to be able to prioritize based on frequency when you detect that a certain kind of crash or a certain kind of instance of a particular crash or particular location in code is problematic, and you have a lot of frequency in a particular kind of report. So the workflow would look something like this. You have your CI/CD infrastructure, either Jenkins or GitLab. We used to use Jenkins. Now we use GitLab runners, but it doesn't matter. And you want in your build scripts, you want to have a step to build artifacts. You want to store, you want to archive these build artifacts. Some of them are important. We'll talk about what. And you want to store them forever, or at least for a long time, for each build that you produce. And these artifacts, for example, for each commit that actually yields a build pipeline, in this case, let's say we have this commit with the git hash C08, and we want to archive symbols for this commit. This would be the dsym file there that I'm pointing at. And you have the standalone tool that is able to process this kind of symbols and user crash reports. So basically, for each build that you pull through the build pipeline, you get your normal build artifacts, your build packages, and what have you. we have several different outputs, but one of them must be an associated archive with all the symbols that you care about for later symbolication. And basically, this dsym file is a zip bundle containing all the PDBs that were built in that particular instance. And this is important because you cannot build these afterwards. These PDB files contain precise information that is entangled with the binary that was produced at the moment that the compiler yielded your output, your final binary. So you cannot later on recreate those PDBs if you go back to the very same commit. You actually need to keep them in sync, entangled, your binary and your PDBs. So that's why you need to actually archive them. A little bit on that later on. If we have time, we'll go more deep into PDB object format and PE and COFF formats, and we'll see how this is relevant. But for the time being, the gist is that you need to have some kind of infrastructure to store these PDB files. And be aware that actually zipping them or compressing them in some way is actually very convenient, because it turns out they actually deflate very well. So you can have a very large PDB basically deflate to less than half its size sometimes. Also, the PDB is the answer to everything, life, universe, and whatever. And you want these PDBs to be full-featured. A few years ago, Microsoft, in efforts to optimize and streamline the debug build cycle, they actually made an option to have a Fastlink phase that produces a streamlined PDB. Basically, it's like an incremental PDB file that is produced, and it's meant mainly for debug cycles. But you need to make sure that you build with full debug capability, basically the legacy PDB. I wouldn't say legacy, but basically the traditional PDB full format. This is the one you want to archive, of course. You don't want to mess with the incremental bits. There are tools that can actually reconstitute a full PDB based on incremental images, but it's way too messy. It's not worth the effort. So you don't want to see basically a dry stack trace, a crash report. This is what you would get from the client side when a crash occurred without having any symbols remotely. So you don't want to see this. You want to make some sense out of a stack trace that you receive from customer support. So you want to be able to figure out, to see file, line number, symbols. You want to see the exact experience that you have in Visual Studio, let's say. So you want to have the exact experience that you have when you're putting a breakpoint and breaking it and seeing the variables, context, and the call stack, everything, even multiple threads, ideally. Okay, and the workflow is very simple. When you have a crash on client side, you have basically a component within the app that actually constructs this information without any symbols and constructs a crash report that is sent over the support service and is collected, is symbolicated and triaged using this tool that we've built. And at the other end, the dev team actually gets a stack trace that looks decent. So a very crude tool that looks like this. You select the build, the target build for that crash. You get it from the build artifacts that you have, the associated dsym bundle that contains your PDBs. And you select the crash report, and you basically get the full stack trace with all the symbols and information, context information that you need. And you get on to fixing the bugs. Sounds very simple, and it really should be that simple. If it's more complicated than this, then it's not worth bothering. So let's see how we go about doing this. And you get something like this. So we have a bunch of information right there. We have the fact that this crash is an access violation. We have the address. We have the fact that it's a write through a null pointer. So we have quite a bit of information right there. And we have the call stack, and we have the exact pinpoint of the location, the source file and line number there. And it's all tied to a particular build. So it's connected to the source control system through the Git hashes. And if we drill down, we see the first clues that we have there. Like I already mentioned, we have the connection to the build system. We know exactly the location. Something to note there, the module base address. We'll talk about this later when we talk about ASLR. But for now, just note that it's important that this be recorded on the client side when the crash actually happens. So we actually do have code into our application that constructs and collects all this information in the crash report when this happens. So it's not like a background component or anything. It's not like a complex runtime. So it doesn't have any cost at all when you're on a happy path. But when a crash does occur, you do pay this cost of constructing this context information on the client side. And the symbolication process happens on the dev side. So how it works? First of all, we have to address the elephant in the room. I know there are several people that would like to see structured exception handling be gone. And I'll grant you that this elephant in the room, it's not pleasant. So I've been dealing with this for 15 years now. And yeah, if you really want to be pedantic and use just standard exceptions, you can for toy projects. But in real world Windows applications, sometimes when you have to deal with the operating system infrastructures and some low-level components and some APIs that need this kind of programming model, you have to deal with structured exception handling. So yeah, it's I think of it a bit like comb. It's not pretty, but it gets the job done. So in real life, true to the metal, close to the operating system applications, structured exception handling is a thing. So we have to somehow address it. So yes, we do use async exceptions on all our modules. You can read more about this. It's a vast topic. I plan to do someday a talk about this. If you want to read more about this, if you're not aware of the intricacies of structured exception handling and all the history, it's a very ancient model, still in place. There are several links there. And by the way, throughout this presentation, I'll have plenty of links and references in the slides. When you get the slides later on, feel free to read up at your own pace. So you do need to, if you want the full experience, you want to enable structured exception handling in the project settings. So they're also called async exceptions. If somewhere you see async, don't be, for example, in the MS build file or project settings. If you see that, it's the same thing. So you want EHA or async exception, the same thing. You want full debug information, so full PDBs, not incremental PDBs. And you want program database information. So this is not truly compatible with debugging continuous scenarios, but those are just for debug configurations anyway. So for release builds, you want a plain program database. That's /ZI switch. And first thing, you want to handle C structured exceptions. Those are the legacy, old-fashioned, let's say, Win32 exceptions. You want to handle those as C++ typed exceptions. And there are functions in the C runtime that Microsoft provides to handle this translation. You have to do a little bit of the work yourself, and I'm going to show you exactly what this entails. But you do have help from the CRP. Again, links, you can read more if you like. So there's an API to set an unhandled exception filter. Again, this is very useful. You might think you got all the exceptions, but there might be places where an exception escapes unhandled. So if you want proper logging or proper context information, and you want to actually catch and fix these kind of crashes, and I'm not talking about recovering from this fatal type of crashes. The process should go down. I'm all for that. But you want some way of actually capturing what happened, capturing some context before the application limps along and crashes. So you want to capture some context and log it or send it to the support channels and investigate it to fix the bug. So this is where unhandled exceptions, we found it very helpful to catch this. And there's a big net to catch this. There's an unhandled exception filter that basically sits basically below main and catches everything that escapes from you, any kind of maybe unstructured exception or something that might escape. So, and this happens if the process is not being debugged. So when you're in the debugger, you're going to catch them anyway in Visual Studio. So we basically intercept all of these. And a handler for this might look like this one. You get, when you're being called by the C runtime, you get an exception pointers structure, and you can trace. You have all the information there. We're going to drill deep into these operating system structures to see how to use them. And you can reach into them and extract all the context information that you need to actually build a full stack trace from an unhandled exception. You see there already we're able to extract the exception code and address. We'll see later on what those might be. And with some helper functions like this one, stack work or trace from context, you can actually build a whole stack trace just from that contextual information that the C runtime gives you. So unhandled exceptions, helpful thing. We actually, over the years, found a lot of things just caught in this net. Wide net, but nevertheless. Also, if we're talking about async exceptions and structured exceptions, those do happen. And you might have an access violation. That would be the most common case. But more mundane cases like overflows, integer overflows, floating point overflows, you're divided by zeros or anything, or unaligned reads, writes, stuff like that. Things like that happen. You wish they weren't happening, but they do happen in real life. So again, very useful. The C runtime provides you a way to actually translate these structured exceptions into, gives you an opportunity to inspect them and translate them into C++ typed exceptions, so that you can consume them and treat them like all the exceptions or the regular exceptions that you might have in your application. By the way, if you haven't figured it by now, I love exceptions. Okay, so first phase, you get an SC code, or structured exception code, and you have to decode it. There are several, I think like 20 or 30 types of structured exception codes, and you have to basically handle all of them. Is just boilerplate code. I'm not showing here, just a little glimpse. By the way, this is slideware. I had to really oversimplify the code that I'm showing here because of space constraints. But the gist carries on. So you basically have to decode to see what kind of structured exception you're dealing with. And for particular kind of exception, the access violation kind, this is one of interest for everybody, basically. You really care about the nature. Like you saw in the core stack that I showed early on, we had like access violation through a null pointer. So all this information is here. So we get to decode this from the structures in the exception pointers. We get the exception information, And there is the operation type, and those magic numbers 0, 1, and 8 there basically tell you that it's either a read or write or a data execution prevention kind of access, causing the access violation. And whether you have or not a virtual address in there tells you that it's through a null pointer or a dangling pointer, or basically a bad pointer. Most people protect against null, the billion-dollar mistake, but you cannot protect for bad pointers unless you sprinkle all your app with shared pointer, which is not a solution, by the way. So dangling pointers do happen. That's life, I guess, but you want to catch them. So this is a way to actually pinpoint that a particular access violation was through a dangling pointer, and you basically encode this in a numeration or something like that, and store this in the crash report. Later on, same function. I'm presenting it piecewise, so it's easier to digest. So after we decode the exception type, again, we encounter our old friend trace from context from Stackwalker. We give it a context record from the exception pointers that the CRT provides us. And we also extract from the same context record, we extract the exception origin, which is the file name and line number. We'll see later on how this has happened. The gist of it being that the C runtime gives us this callback, and we can hook into this mechanism, and it gives us, through the exception pointer structure, it gives us a way to mine all the information on the client side and construct a C++ typed exception here. It's called SEH exception. You can use whatever exception type you want, standard exception, whatever you want, and throw it after the C runtime gives you an opportunity to handle it. Throw it like a regular C++ exception and catch it and handle it however you like. Log it, ignore it, whatever. I wouldn't try to recover it. What? So this would be the gist of the SEH translator, translating from a structured exception into a C++ typed exception. That's it. What about an exception in flight? So you want to get a stack trace for the raised exception on the current thread. So you're on a catch block, let's say, or somewhere, and there's an exception in flight, and you want a snapshot of the stack trace in that particular location, maybe to log it, I don't know. There's a way you can do that. Here, I have a very simple function, get stack trace for current exception. And again, we see our old friend, Stackwalker trace from context, which we'll get to later on. And we give it the GetCurrentExceptionContext. So we have to figure out somehow from an in-flight exception to figure out on a particular thread, mind you, to figure out the execution context. That very same thing that we got from the CRT, for example, when a structured exception happened, or when an unhandled exception happened. So the very same thing, the execution context, that is the very rich information that we need. It includes everything, even computer register information. You want to capture that somehow for an in-flight exception. And this is where this GetCurrentExceptionContext helper function comes in. And let's see how it looks. So it gives us this PContext, this structure that we've seen before. And it contains processor-specific register data, register values, and various flags that you can mine for particular interesting bits. Again, if you want to read more about this structure and how it's used, there's a link there. But we've seen this one, so we know how to deal with it. So we've seen it in the translator function, that the callback that we used for the CRT hook. And again, this exception record, in that case, was wrapped in this exception pointer structure that we've seen, that the CRT fills in for us. So we have this PContext right there alongside the exception record. The exception record we already mined when we figured out information about, is this access violation, what kind of access violation is, what's the virtual address, easy to read, easy to write, blah, blah, blah. So what's this context? How do we get this for an invite exception? First, let's see the exception record, because we already used some of the fields in there, but let's see what's in there, really. So you do have the exception code, the flags. We already see that this is a linked list of exception records. This is mainly how it's treated for x86 architecture in Windows. For 64-bit architecture, the model is a little bit different. There's a lookup mechanism as opposed to a linked list traversal, so it's more efficient in the unhappy path. It's a little bit more efficient on 64-bit. Other than that, the structure looks mostly the same. If you contrast the explicit 32-bit and 64-bit structures that the Windows SDK defines for us, you see that that pointer of different size is there and depicts the exception record, and it either points to a table or a linked list. It's not important. How do we get this P context? So if you're a newish Visual Studio that is 2015 or later, so I'm guessing everyone, this is the magic incantation to get that. Don't ask me how I found out. I really don't remember. Maybe Googling or I don't know, mining the dark corners of the internet. I don't remember. This happened, I think, years ago. Really years ago. So I don't remember all the information. It's a little bit fuzzy. It really doesn't matter. Just take it as a magic incantation and test it and see that it works. And disclosure, it uses private, undocumented APIs. So, but Microsoft has a pretty good track record of actually being very stable with the private APIs, and they basically never change. So we've been using this technique, and I have a slide for all the Visual Studio versions. So we've been using this technique for over 10 years now, and we never had to change code when something changed in Windows or in SDK. So it's pretty stable, but it's uncharted territory there. So you won't find MSDN links, MSDN information. So sometimes the structures, I remember one of the structures that I'm going to show you, I basically found it on some Google group somewhere. Somebody pasted that. They figured that I think I found some structure in the Chromium source base for the 64-bit. Yeah, I remember for the 64-bit case, I found a structure in the Chromium code base that's basically someone reverse engineered and figured out the structure layout and what's in there. So magic. So take it as it is. It works. Test it. Okay, so you have some helper functions from the CRT, current exception context, and here you have to differentiate in either if you do static link or dynamic link for this module. So if you, and in this time I'm referring to how you link against the CRT. So if you static link the CRT into your application, then you're on the else branch here. If you're dynamically linking to the CRT, then you're on the first branch, on the if branch. So you have two helper functions from the CRT, again, private APIs that do all the magic for you. And you retrieve from this again a non-documented structure, internal structure, this VCRT PTD, and it contains the current context. So this is how you get that most wanted P context. If you just to mention, maybe some of you are stuck in an older version. We've been using this code when we were on Visual Studio 2013. For some time now, we had used both toolchain versions, 2013 and 2015 for period, because we had to target older operating systems and life. So this is the code we used on 2013. basically a similar incantation, a different CRT structure that contains the PContext, and different CRT functions, again, private APIs that get you there. Just take it as it is. Some headers of interest, eh.h, exception handling, signal.h to access these functions, and some function prototypes and private includes that you shouldn't theoretically touch, but those are there. And I think this is the structure. Yeah, if I remember correctly, I think this is the structure that I had to patch for when we started building for 64-bit application, the 64-bit version of our application. So I think this is the structure that, if I remember correctly from years ago, that I found in the Chromium source code or something. It's I found the magic fields there. It's a little blurry, but it's not meant to be understood. Okay, so so we've seen how to get the context for an in-flight exception. But what if we want to get the stack trace from the context of a caller? That is to get a stack trace on demand, no exception is in flight, nothing crashed. You just want some rich logging. For example, maybe you have an assertion that you want to print a stack trace of an assertion when it happens, or maybe you want to log a particular place, a particular location that is called to see which are all the paths that you reach to reach that function, and when something, I don't know, some invariant is broken. I don't know. It turns out to be very useful, even without the context of exception. How do you get a PContext from the caller function? So no exception. And here there's an API in kernel 32. It's called RtlCaptureContext. Very easy. You dynamically load it. If you're on newer Windows versions, you don't have to bother with the dynamic load. You basically can invoke it directly. I think there's a signature in the SDK for it. Don't remember. But you can always dynamically load it. And you do capture context and you get the context. And then our old friend trace from context does the heavy lifting and builds the stack trace with all the symbol information. So now that we know how to get this PContext, how do we walk the stack? So starting from this very simple structure, how do we traverse the stack and build each stack frame and see what's in there? So let's see this old friend that we've used all these slides, in all these slides. So trace from context. By the way, the API that we're using here, the stack walk API, and most of the APIs that deal with debugging tools or ImageHlp library, all these APIs are single-threaded. So if you're doing any kind of multi-threaded stuff, you need to be aware that you protect this type of function and this type of processing, and needs to be in some kind of critical section to be protected. So just as a warning. And you have to copy the context structure because the stack walk API actually stumps over it. So you have to make a copy of this structure. You cannot reuse the same pointer that you have. So you have to save it. And you get your context, you get the current process, current thread. This is easy. Again, we have a little helper here. We have a class that acts as a symbol explorer. And this would be the one that maps the information to the debug information. This happens on our side when we actually try to symbolicate and rehydrate those dry crash reports. So on the client side, this symbol explorer does nothing because it has no symbols. It basically constructs just the dry crash report without any symbol information, but with the right addresses, and the PContext is valid. It has all the good information there. So after that initial setup, you get your main for loop there, and you have a stack frame structure. And I'm omitting here. There's a platform dependent, an architecture dependent init phase. This init stack from context. You have to set up the stack frame in a particular way. I think I omitted the slide that does that. Maybe I'll include it when I publish the slides later on. You have to fill in some fields with some magic numbers, and it just works. This bit is actually documented. So it's a public API. It's not something like undocumented territory there. So you have your frame for loop and the stack walk API that actually starts from the current context there that you received somehow from an in-flight exception, from a caller or whatever. And you have that context information, and this stack walk API basically traverses each call, each frame. And we have our friend, the Symbolicated explorer there that composes each stack frame for a given offset. So for a given program counter, that PC is program counter. So for a particular program counter, you have the offset, which is the function address, and you can record this information in your crash dump. If you have symbols, it will put symbols information there. If you don't have symbols, like on the client side, it will omit those. And you can use the same infrastructure to rehydrate and symbolicate applications on the dev machine or on a support client side. And at the end, very important, you have to write the module load address. And this is needed because of SLR. And this, if someone is not aware about this, each time as a security measure, in the old days, the modules were loaded at the same address in a parent process, and even a process that is spawned was always basically spawned deterministically at the same address in virtual memory. So this actually changed a few years ago, I think, with Vista, if I remember correctly, with Windows Vista. So basically, you have a subsystem in Windows that basically randomizes the base address where the process is loaded or a module is loaded in your process. So to prevent patching or trampolines or something like that. So it's a security measure, and you have to record. We have to record this precious information because it's a random thing. We have to record this module base address on the client side. So later on, when we figure out all the function addresses of our module, and we also always have to figure out a displacement and use this load address, base address as a baseline for address arithmetic when we calculate the real address to figure out the symbol names in the PDB. So very important to capture this information on the client side. This composed stack frame from the symbol explorer is very simple. You have this, the address, again, two helper functions, symbol name from address, and symbol source from address that gives the name and file names, file line. Very simple, trivial. And symbol name from address uses this API from the Debug Help Library. You see there, DbgHelp.dll. You have the API sim from address. And you basically use this to get, if you have symbols loaded, and we'll see how to set up symbol paths and everything. And we need the system to reach these symbols. You basically get a demangled function name. So that pretty name that you actually want and the thing that you see in your debugger when you're debugging on your machine. So you get all that information just with this very simple API. This is basically the whole code. I cut very little from this function. And to get the file name and file number, line number, again, there's an API, sim get line from address, and you have a displacement, and you give it the program counter, and it gives you the right information from the symbol source. Again, mostly boilerplate. It's not anything fancy here. This is the part where you compute the randomized base address loaded. This is the code that needs to run on the client side. So you have to get the module handle, and the module handle basically represents the load address that the module has been loaded at. And you have to recode this somewhere in the crash report. The init phase, again, a little dance, some boilerplate that you can find on the MSDN. This part is documented pretty well. You have the sim initialize phase, and the important bit here being the function that sets the symbol search path, because you can give it a location. This is the argument here being the location where we have stored those PDBs. Remember that the build artifacts that we store, that we archive for each build, and we store them. We have a way, the tool has a way to get there, reach there, get the DSym archive, unzip it, and point this symbol util class, point it at the symbol path there to find the appropriate PDB. And the symbol search path, basically, if it's given a path, it uses it for using this API symset search path, which is a documented API, pretty straightforward. It has some remarks and rules and corner cases, but if you point it at a symbol path, it basically prioritizes that thing, and it has some fallback search locations where it searches for symbol information if you don't provide it a path, or if it doesn't find an appropriate PDB in that path. And as a fallback, you can always assume that you have a PDB next to the executable there. That's the bit in the if branch here. Okay, so all this dance was nice. Might sound pretty complicated, but it's actually not that much code. But there's a good alternative. If I didn't sell you on this path, and you're not convinced that this might actually help you, and or maybe you consider it to be too much work, it works, but might be a turnoff. I can see that. There's a good alternative that you should be aware of. If you're on a fairly recent version of Visual Studio 2019, I strongly recommend that you be on the latest. There's a newer thing. Actually, the Minidump file format is fairly old, but the recent Visual Studio versions actually put this on steroids, and it really is a game changer. It makes everything better. So the Windows snapshot process can capture program virtual memory and heap and lots of other metadata from an application that crashes, and you can wrap this in this Minidump file, and Visual Studio can parse this, and the latest Visual Studio versions have a pretty nice user interface, user experience around using the snapshot files. So you can parse them and open them in Visual Studio and point to the right location, give you the code stack, the context information, all the variables and everything. And I think if more people embrace this kind of format, and this one is basically in the box, it's a tool standard. It comes with the latest Visual Studio. If more people embrace this kind of format, I think it will make for a better experience debugging applications and reporting bugs in general. And if you combine this with live share, I think it's amazing. So this is like a Minidump summary. This is how it looks like. And you open it in Visual Studio, and you basically have a debug experience like you had set a breakpoint there yourself. And you can even start a collaborative session right there from that breakpoint in the snapshot file. In Init a live share session when you can do pair investigation with somebody else on a different computer. If you don't know about live share, just search it later on and see how live share works. It's amazing, and it works Visual Studio to Visual Studio, Visual Studio to VS Code. It's amazing. It's a great tool to collaborate and investigate these kinds of bugs that don't happen necessarily on your machine. So there's a potential there to be something that might pique your interest. So in the end, we have to think about post-pandemic crashes and what we'll do to handle stack traces in 8 years to come. So there is actually a fairly old by now proposal, 881. First draft is from 2018, actually, and it's based on Boost StackTrace. If any of you are familiar with Boost StackTrace, it went through several revisions. Now it's at revision 7. It's a very good paper. I enjoyed tracking the progress through the standardization process. Unfortunately, it didn't make it into C++20. I really hoped it would, but it didn't. So it definitely will make it into 23. So again, I chose some names for the thing we built. the library proposal investigates several names. I don't know if you're going to be happy with the one that is going to win. It doesn't really matter. What matters is that you're going to have a portable way to construct such stack traces and capture this kind of information from your application, and it will work everywhere. And it will be much more pleasant to use than the bits I've shown you up until now. So this will be the first major library feature that will be in C++23. So it's basically voted in. It's basically there, just some polish. And key features desired, all functions are lazy, so you don't want to query StackTrace entry information without explicit request. Same thing I told you earlier, stuff that you do on a client, stuff that you have to do when you have to process these things. Dynamic size for stack traces, so you must not assume that a stack trace is limited by a given depth there. So you have to be able to enable, disable this machinery through a linker switch. So compiler vendors, tool vendors will have to give you a way to opt in into this mechanism. And of course, you shouldn't pay for this kind of facilities. So it shouldn't prevent the compiler doing any optimizations in the presence of these functions that are around your code. So and should be because they're meant to be very lightweight. They should be usable in contract violation handlers, in coroutines, in any handler functions, in threads, in parallel algorithms. So they should be able to be usable everywhere. You have a stack trace description that return a demangled function signature. We've seen this already. You have helper functions like toString to get the debug symbols information and other resources and show demangled signatures. It should have support for inline functions and display entries for functions that have been inlined in the final binary. I think that is just merely guidance in the spec, and should avoid doing any heavy operations in the constructors and the factory function, the static function current. So it should be fairly quick to invoke. This is the important bits, the salient bits from the class. It has a lot of functions and operators and needed boilerplate. But these would be the salient bits: description, source file, line, way to get a native handle, something to the native implementation from the vendor. And it models the regular and it's comparable. A backtrace has basically a way to store stack trace entries. It's not required to be a vector, but a way to store several frames, and the frames are of type stack trace entry. And you have a way to traverse them, and it has again configurable allocator that it passes to the frame. You can get, this is how you get the stack trace. You get the current stack trace. You can skip over some frames, and this is how you would initiate and get a hold of a stack trace on the current thread of execution. Sorry. You have the helper functions to string. You have the IOStream operators to log easily. All the boilerplate that you need to construct to make something like this usable, like get the current stack trace, do a range 4, and print the description, source file name, file line, or even simpler, to use toString from the stack entry, which has this overload, or just print out the frame directly to an IOStream. Or even simpler, to print out the whole backtrace without individually printing the frames. So it magically works. So this is you couldn't get any simpler than this. So when we get this, I'm hoping it will become available pretty soon, even before 23. So I'm hoping that library implementers will provide this as soon as possible. I'm hoping that everyone will jump on board and start using this kind of facility. Maybe migrate your own homebrew implementation like we have. We're definitely going to try to see if we can switch to this implementation when it becomes a de facto standard. With that, I'm ready for quick Q&A. I'm going to switch to Remo now.